So the project we decided to do is an automated fan and humidifier system. My name is Michael, and this is I'm with my partner, Aidan, and our team name is FCS for the sake of grading. So the material we'll be using for this project is a LM335 temperature sensor, as well as the Jessini humidity sensor. And we will also be using two STM32 Nucleo boards simply because I have the different uh, board. I have the L432KC and Aidan used a different one. I think it was the F303. We'll also be using a potentiometer for the thermal sensor, an LED, 330 ohm pull-up resistor, a voltmeter, and some jumper wires. So for our project, this is basically the block diagram for everything that we're going to be setting up. We have our thermal sensor connected to the MCU, as well as the moisture sensor connected to the MCU, and then their associated peripherals, which turn on a fan or an atomizer. For this FSM, we will be using a slightly different variant of this because the idle state splits into two states, which handle temperature and humidity respectively, which is a little bit different than what we did in the lab 2 for the traffic light system, because in the traffic light system, we only had the idle state going, or we only had one state going to another based on one parameter, which was time. But in this case, the idle state moves on to either the temperature reading or the moisture reading. And the higher priority goes to the one where the parameter is basically reached first. So if the moisture in the atmosphere is 60% before, we get to a temperature that's warmer than the room temperature, then we're going to move straight to the atomizer turning on. So that's the gist of the FSM. The LM335 sensor operates from 2.92 volts to 3.04 volts, and it has a minimum error of, as you can see here, 1 degree Celsius, and that assumes that you could calibrate this thing to 1 milliamp, which in my case was pretty much impossible because I don't have the equipment for that, but I was able to use the potentiometer to actually, reduce the 3.3 volt pin down to a 3 volt. And so I was able to get it to work properly that way. And so for setting up the ADC, I actually ended up using a slightly different variation of our ADC formula from class, which is that I simply added an N ratio to the ADC reading and the analog voltage, because the LM335 sensor only measures 1.4 volts for the actual total range of the temperatures. And here's my pinout view for everything. I just had the ADC set up for A3, the fan set as an output pin, and then just UART kind of running as its own within the software. The internal software wasn't actually connected to any pins, even though that's what it looks like. And this was my code for the while loop, which is what it basically runs consistently. And though you can't actually see what's going on with the states, the value of the voltage gets thrown into this function called state capture, where state capture actually goes through all 3 states for the temperature sensor. And that was basically everything on my part.
All right, so for me, I set up the ADC for the humidity sensor, and I got that thing working. So the humidity sensor works by simply outputting a analog voltage depending on the local humidity level. No libraries, no I squared C. It just takes 5 volts in, it outputs 0 to 3 volts depending on the local humidity value. So this is pretty convenient for me. So I found it useful for that reason. So we then use the ADC port on the STM32, which if you would, in one of the next slides, you'll see which port it's at. But we use that to read the output voltage. We then later use the formula humidity equals the output voltage over 0.03 RH, which is the relative humidity. This will give you the percent local humidity. This is the data sheet for the humidity sensor. Now, you don't need to read most of it. Just look at 6.2, where it says the relationship between humidity and output voltage. It's the formula I just mentioned. And under that is a linear graph of it. Through my own personal testing, I was able to measure a voltage that corresponded with these values. Of course, I don't have another sensor to measure humidity, so perhaps there could be some error there, but I found it to be pretty consistent with little error. All right, then this is my pinout view for the humidity sensor. I have PA0 as the ADC input. I have PA1 as the GPIO output, which is what would power the dehumidifier based on the current state and the user input of the humidity. And this is the humidity sensor code. So a lot of it is pretty similar to Michael, except I have it printing to UART through UART to the MOBA extern program so I could read what the program is, picking up. And I have a voltage to humidity conversion, which I already talked about earlier. And you can see the formula there again. And at the very bottom, you can see that we used an interrupt to force the program to check and change states based off the local humidity that I was picking up. And if it was above 45 in this case, it would turn on the dehumidifier. So we went over that, all this stuff, but it was not all sunshine and rainbows. We had some issues, particularly with the DH11 sensor. We weren't able to get it to work easily. We realized we would need to use a bunch of I was it I square C? Yeah, that's
I
what it
believe
was.
so.
And for me anyway, I just couldn't get the hang of that. And you have project deadlines, we had to get it done. So I found a new sensor, which I just talked about, and it made things much easier. Building the FSM caused me some issues because I had a hard time getting an if statement to work with that stuff. And Michael has some issues with the Raspberry Pi. So in conclusion, this is quite obviously a work in progress. I actually do not have a dehumidifier currently, but I have a working output. So all I need to do is just buy the part and hook it up. Some other things about this project is honestly, me and Michael both wished, obviously once the code is perfect, to be able to make this on a bigger scale so we can actually see it kind of
Yeah,
working or sense it,
yeah.
sense the air getting cooler or less damp. And at the very end of this conclusion, we have a question for you guys. How might this project be a little bit simpler or complex? We're not sure actually, we haven't done it, if we were to use an Arduino MCU. And last but not least, these are the data sheets for both our sensors. You can go ahead and look through more of the details that you want. There was some pages we obviously didn't show, but I don't think those pages were as relevant. They are there.
Right, I hope you guys thoroughly enjoyed our presentation, and yeah, please give us a good grade.